We just learned the formula nth root of a equals a to the 1 over nth power. Now, we can just, for convenience, so that we don't have any notation clash, replace all the a's with z's and all the n's with k's. So this is the same formula. Kth root of z equals z to the 1 over k. That's the same. And what we're about to do now is take some radical formulas that we've seen so far in these slides and take some exponent formulas we've seen previously and now lead to some new formulas. So previously we have seen these formulas, ab to the, I think we had nth power before, but I've changed it to an s. But same deal. Okay, ab quantity raised to the s equals a to the s times b to the s. We also previously saw with a different variable, a over b quantity raised to the s equals a to the s over b to the s, and we've also seen a to the r quantity raised to the s equals a to the rs. Again, instead of with s as the exponent, I think we've typically seen these with n's or m's, but same deal. And what we're going to do is take one of these formulas at a time. There are three bulleted formulas here. We're going to take one of these exponent formulas, which we have already argued to be true. So these three formulas we should trust, but we're going to start with these and then create new formulas. What we're going to do in each case is substitute every s with a 1 over n and substitute every r with a 1 over m. And then we're going to apply this new formula that's at the top of the slide, kth root of z equals z to the 1 over k. And that's going to give us a new radical formula. So from this exponent, the first exponent formula on the first bullet, we'll get a new radical formula. From the second exponent formula here, we're going to get a new radical formula. And from the third exponent formula, we're going to get a third radical formula. So why does this work? Well, we're starting from a formula which we already know to be true from last time. Then we're substituting. And then we're applying another formula, this one up here, this kth root of z equals z to the 1 over k, that we had just shown was true. And in the end, we're going to get a new true formula each time, whichever one of these three we start with. So let's go through that. We'll start with answering why is the nth root of ab, that is the nth root of a times b, why is that equal to nth root of a times nth root of b? Why is that true? So previously, we saw ab raised to the s equals a to the s times b to the s. We have already argued why that is true. We trust this formula. And now we do this substitution. Replace every s with 1 over n. Okay, so plug in 1 over n everywhere you see an s. So we're going to write this equation here, ab to the s equals a to the s, b to the s, except we're making that little replacement. Every s that was up here became a 1 over nth power. So those are all exponents. And now we're going to apply kth root of z equals z to the 1 over k. But I guess in reverse. What we have are things that look like this, z to the 1 over k, and we're going to turn them into kth root of z. So on the right side, this a to the 1 over nth power is going to become nth root of a. Also on the right side, b to the 1 over nth power. So now look, b is going to take the place of z. And n, that's what we plug in for the k. And then we'll see that b to the 1 over nth power, due to this new formula, is going to become nth root of b. On the left side as well, this one's a little more complicated, but there's ab raised to the 1 over nth power. So for this formula, we are plugging in k. For the k, we're plugging in n, and for the z, we're plugging in ab. And then turning that into what's on the left side of this formula, we end up with nth root of ab. So this entire equation, making three replacements, we talked about the two uses of this new formula on the right side first, just because they're the easier side. We end up with nth root of ab equals nth root of a times nth root of b, and that is the formula up at the top. We have just argued that this formula is true. I know this looks like a long-winded process, but really it was start with an old formula, the exponent formula from last time, make a substitution, and apply a new formula three times. Okay, what about nth root of a over b equals nth root of a over nth root of b? Why is this true? In other words, if we look at what this formula is really trying to communicate, if you have a fraction inside a radical, it is allowed for you to split that radical and write two separate radicals, one in the numerator, one in the denominator. That way you could simplify further. So why does this work? We previously saw a over b raised to the s equals a to the s over b to the s. Same deal, substitute 1 over n everywhere you see an s. And then apply this new formula that a kth root is the same as a 1 over kth power, just in reverse again. And on the right side, in the numerator, there's this a to the 1 over nth. That's going to become nth root of a. In the denominator on the right side, a b to the 1 over nth power is going to become an nth root of b. And finally, on the left side, using the formula plugging in a over b for the z, we're going to get that the left side is going to become nth root of the fraction a over b. So ultimately, in the end, making those replacements due to the a recent-ish formula, we're going to have nth root of a over b equals nth root of a over nth root of b. One last one. This one looks a little funky, but why is the nth root of the mth root of a equal to the mnth root of a? So we previously saw a to the rth quantity to the s equals a to the rs power. That is a formula we've already argued why it's true, and we trust it. We're going to substitute now not just for s, but for r as well. So for s, we're going to replace with 1 over n. Every r, we will replace with 1 over m. And so then this previous true formula, which we trust, once we plug in consistently, every s became a 1 over n, every r became a 1 over m, then we get a new thing that we trust, as funky as it looks. Then we will do this 1 over m times 1 over n. We can turn that into 1 over mn, just using our fraction multiplication rule, multiply straight across. And on the left side, just taking it one step at a time, the 1 over nth power, using our new formula, becomes an nth root. And then inside the radical, there's a 1 over mth power, and so that can become an mth root. On the right side, which we haven't done anything with for a couple steps, there's a 1 over mn as an exponent. And recall, just like over on the left side, when you have a exponent which is a fraction, and that fraction is 1 over something, that denominator, in this case mn, becomes the little number right outside the radical. So mnth root of a. So let's just summarize and see where we got, what did we do? We started from 3 exponent formulas, which we already knew were true from a previous time, and we got these 3 new radical formulas. In the first formula, right here, now we have this new formula we trust, but if we plug in n equals 2, so there are 3 places where there's n, once on the left and twice on the right. If we plug in 2 for all the n's, then you'll have this, the second root of ab equals the second root of a times the second root of b. Of course, if you want, you don't have to write the little 2's, right? So whenever a little number is missing just right outside the radical, that hidden number is a 2, so we can skip writing it. The point is root ab equals root a times root b. You don't have to memorize root ab equals root a times root b separately. It's just a special case of this nth root version over here. But this formula is nice. What this formula is about is saying if you have root and then things multiplied together, the key word here is multiplied, then you can split it up. You can take that expression and replace it. You can simplify it as root a times root b separately, and then you'd be able to simplify each of those 2 pieces separately. Okay, now this formula right here, root ab equals root a times root b, I just want to really clarify something. So I'd like to, for emphasis, really draw in the multiplication signs. I've drawn them in big. So down at the bottom of slide number 19, this is really the same as what's in the middle of slide 19. I just drew in the multiplication symbols to try to illustrate a point. Here's the key thing to really be careful of. It is true, we just saw just a moment ago, that root a times b equals root a times root b. That's true. But root a plus b equals root a plus root b? No, that is false. So in other words, square root does not distribute, at least not when you have this plus sign here. Let's just make sure. So typical question. I know it's already up here in red that this is false, but let's just form this as a typical question for a quiz, for instance. Is root a plus b equal to root a plus root b? True or false? Explain why. We already saw it was given away that this is false, but let's pick some nice numbers for computation. For instance, I'll pick a equals 16 and b equals 9, and the left side is root 16 plus 9. Don't apply the formula in question. The formula in question is asking, is it okay to distribute a square root sign? So don't actually do that while we're trying to talk about it. Instead, just simplify 16 plus 9. So don't distribute the square root sign here. we're trying to argue whether that's an okay thing to do or not. So you have root 25, and that'll simplify to plain old 5. On the right side, you have root 16 plus root 9, so you'll get 4 plus 3, which simplifies to 7. The left and right sides are not equal, right? When we picked a equals 16 and b equals 9. Therefore, this formula can't be trusted. Root a plus b equals root a plus root b? No, that's false. That's a lie, and we should not believe it. Okay, instead, root a times b equals root a times root b. We saw that that was true because it ultimately grew out of an exponent formula and just some substitutions. So here's your interactive question. Visually, what's similar and what's different about the true formula and the false formula? Okay, this is asking you for your opinion about how these formulas look. So please try to include as many details as you can to try to keep this active and make it so that you don't make the mistake of using the false formula.